At nearly 11,000 meters down, creatures twist into giants, some with jaws that snap in a blink, others swollen 13 times their shallow kin. At this depth, NOAA research finds pressure shatters bones and cold rewrites life's code, turning evolution itself monstrous. Yet none of this explains why the abyss demands such terror. What force in the deep is mutating size and shape, making giants ever more nightmarish the darker it gets? Far below the reach of sunlight, the laws of biology twist into something unfamiliar. In the deep sea, cold acts as a slow-motion clock, stretching out growth for decades. Scarcity and isolation turn the abyss into an evolutionary island, where normal rules break and size itself becomes a survival tool. Here, predators thin out and competition fades, letting some creatures grow to sizes impossible in crowded, warmer waters. Metabolic scaling takes over. Lower temperatures slow every heartbeat and every cell division, allowing bodies to accumulate mass over years instead of months. Giant isopods, for example, can reach half a meter long, while their shallow relatives barely span a thumb. In this world, the few that can endure the famine and pressure trade speed for bulk, becoming living vaults of energy. As one Huddle ecologist put it, down here, time and space stretch, and so do the animals. This is not just a quirk of chance, but a pattern. Wherever the ocean grows deep and cold, giants wait in the dark, shaped by the math of metabolism and the silence of the abyss. Giant isopods haunt the seafloor like armored relics, their bodies swollen and pale in the dim light. When a whale carcass or sunken fish finally lands, the feast begins. Dozens pile over the remains, tearing flesh with jaws built for endurance, not speed. Each isopod can gorge until its segmented shell strains at the joints, storing enough food to survive weeks or even months of famine. This is feast and famine physiology in its purest form. Slow metabolism and immense gut capacity are a design for a world where meals are rare and unpredictable. Deep-sea amphipods, too, push the limits of size. In the trenches of the Pacific, some species grow up to 13 times larger than their shallow water cousins, thriving where pressure would crush most life. The deeper the abyss, the more these scavenger giants dominate, their bulk a living answer to the question of why deep-sea creatures grow. Survival here is not about speed or strength, but about becoming a vault of stored energy, waiting out the darkness until the next meal falls from above. Lanternfish drift in the blackness by the billions, each carrying a row of glowing spots along its belly. These photophores are more than decorations. They are camouflage, tuned to match the faint shimmer of light from the surface above. By lighting up their undersides, lanternfish erase their own shadows, vanishing from predators lurking below. Every night, they rise hundreds of meters toward the surface, feeding on plankton and tiny crustaceans. Before dawn, they retreat again, carrying the energy of the surface down into the deep. This nightly migration is the largest animal movement on Earth, a vertical highway that links sunlit waters to the abyss. In the process, lanternfish transport carbon and nutrients into the midnight zone, feeding squids, deep-sea fishes, and even the giants waiting below. Each glowing body becomes a moving target, a signal and a shield, in a place where being seen can mean sudden death. The deeper the migration, the more the rules of predation and survival twist into something stranger, setting the stage for predators built to hunt in absolute darkness. A pale shape drifts through the midnight zone, almost boneless in its slow motion. The goblin shark waits, its body slack, conserving every ounce of energy. Beneath that stillness, a hidden weapon is primed. When prey wanders close, the jaws unhinge, powered by elastic ligaments wound tight like springs. In a flash, less than a blink, the entire jaw apparatus launches forward, shooting out from the face with a force driven by stored tension, not muscle alone. High-speed biomechanical analysis reveals the jaw can fire in just milliseconds, a slingshot strike that turns sluggishness into sudden violence. This is predatory adaptation at its most extreme, a design that lets the shark ambush without wasting energy, perfect for a world where every meal is rare and every movement must count. One biomechanics specialist said, "Down here, the monsters don't chase, they wait and then let physics do the killing." Deep in the Southern Ocean, a shape looms that dwarfs almost any predator on Earth. The colossal squid, Mesonychoteuthis hamiltoni, is not a myth or a sailor's exaggeration. In 2007, a specimen weighing nearly 495 kilograms was hauled from the Ross Sea, its bulk nearly half a ton of living muscle and weaponry. Unlike its giant cousin, the colossal squid hunts with arms lined in swiveling hooks, each one capable of rotating as it grips, turning struggling prey into a tangled prize. Its eyes are the largest of any known animal, spanning up to 27 centimeters across, built to detect the faintest glimmer of movement in the pitch black. Down here, size is not just for intimidation. It is a tactic. Immense eyes to catch the briefest flicker, massive arms to seize what little life passes by. In the abyss, the colossal squid is proof that the deeper you go, the more monstrous survival becomes. In the black waters north of Greenland, a shadow glides so slowly it seems to belong to another era. The Greenland shark, Somniosus microcephalus, is a living relic of patience, growing just a few centimeters each year and outlasting generations of surface life. Radiocarbon dating of eye lens proteins has revealed individuals at least 272 years old, with the largest likely approaching 4 centuries. Some models even suggest lifespans beyond 500 years. These sharks reach maturity after 150 years, drifting through darkness as time itself slows in their veins. In this world of near-freezing water and endless night, survival is measured not in speed or strength, but in centuries of stillness. The Greenland shark is not just a predator, but a witness, its body marked by the slow grind of deep sea time, a strategy that lets it endure where almost nothing else dares to linger. At the edge of the Hadal world, the rules of survival are rewritten by chemistry. Here, every vertebrate faces an invisible barrier, not of stone, but of molecules. In a lab lined with high-pressure chambers and dissected trench fish, a molecular biologist traces the arc of a single compound, trimethylamine N-oxide, known as TMAO. With each kilometer of descent, TMAO builds up in muscle and blood, bracing proteins against the crushing weight. It acts like a molecular scaffold, holding the machinery of life together as pressure climbs past 1,100 atmospheres. But there is a cost. TMAO is also a salt, and every extra molecule raises the concentration inside cells, bringing it ever closer to the saltiness of seawater itself. Data from NOAA research and MBRI studies show a nearly perfect line. The deeper the fish, the more TMAO it carries. By 8,000 meters, Hadal's snailfish are nearly isosmotic with the ocean around them. Push just a few hundred meters deeper, and the chemistry flips. Their bodies would become saltier than the sea, unable to keep water out. No vertebrate has ever been found alive beyond 8,200 meters. This is the biochemical ceiling, an unseen wall drawn by evolution and enforced by the physics of water and pressure, where the giants of the abyss must finally stop. Past the TMAO barrier, the trenches become a world where vertebrate rules no longer apply. In the Kermadec and Tonga trenches, each plunging well beyond 10,000 meters, the abyssal plain gives way to narrow valleys lined with soft sediment and exposed slabs, pressed by over 1,100 atmospheres of pressure and chilled to just above freezing. Here, the dominant life forms are not fish, but invertebrate swarms, amphipods with glassy shells, holothurians drifting like pale ghosts, and polychaetae, worms that tunnel through mud untouched by sunlight. When a lander drops bait into the trench, amphipods arrive in dense clouds, stripping flesh from bone in minutes. These scavengers reach sizes that dwarf their shallow relatives, thriving on the edge of what biochemistry allows. In rare pockets, hydrothermal and cold seep vents break through the trench floor, releasing plumes of hydrogen sulfide and methane. Chemotrophic bacteria bloom around these seeps, forming mats that anchor entire food webs without a trace of sunlight. Tube worms and clams cluster in the chemical haze, their bodies fed by microbial partners that turn toxic gases into life. This is a world built on geochemical energy, not photosynthesis, a patchwork of ecosystems that ignore the vertebrate blueprint and flourish in the planet's deepest, most hostile places. For the scientists who lead Hadal expeditions, every dive reveals new forms and strategies, hinting that the rules of survival here are still being written. Right now, the deepest trenches hide creatures science has never seen, where TEMAO molecules and evolutionary pressure forge monsters beyond imagination. Every NOAA research dive and MBARI study reveals only fragments. Deep sea science explained one terror. Millions remain. Share your theories below. What else waits below 36,000 feet? Still unseen.